Hi, I'm Casey Salguero,
And I'm Andy Wagner.
and we are the team for the Automated Precision Agricultural Device for Monitoring Sustainable Farming Systems. So to talk about the issue that we're tackling, monocropping is one of the most traditional forms of crop growing, and this is when you only grow one crop type repeatedly, and this method, over time, depletes the soil and land of its nutrients and fertility after several years. And because of this, the land can become unusable and unable to grow life. So to fix this issue, farmers need to switch to more sustainable farming systems, but they're hesitant to do so mostly because these systems are more complex and they require much more monitoring and labor, which is where our solution comes in. And our device is meant to assist in the labor and the care of the farm that would otherwise need to be done by hand. So for our solution, the APABot is a self-driven robot that includes environmental sensors, obstacle avoidance software and hardware, and a weed identifying camera. So the environmental sensors included measure temperature, humidity, atmospheric pressure, and soil moisture. And the obstacle avoidance feature also includes a distance measuring sensor that forces the robot to change direction when it gets close enough to an obstacle. And finally, the weed identifying camera is a camera that is controlled by a small computer that is programmed to detect various types of weeds. The device will also send this sensor data as well as device status updates to a user interface for the farmer to use and view. And pictured is the current prototype of the APABot. You can see in the very front is our distance sensor for our obstacle avoidance system. And at the very top is one of our environmental sensors that measure temperature, humidity, and pressure. So for our sensor network and obstacle avoidance system, one of our two main computers powers, commands, and receives data from the environmental sensors, which are separated into two sensors. The first sensor that was pictured previously is a combination sensor that measures the temperature, humidity, and pressure, while the second one only measures soil moisture. The same computer also controls the drive system, which includes the wheel motors and the distance sensor. The motors are programmed to react to the distance sensor so that when an object comes within range, the wheels stop and change direction. Shown below are examples of outputs from the environmental sensors and the distance sensor. So these outputs were able to prove the accuracy in the sensors as well as their successful implementation.
So in order to identify weeds in the fields, we use machine learning to teach the computer to recognize weeds. And we do this by gathering images of 3 common New England weeds: dandelions, poison ivy, and clover. We then take these images and train the device using a machine learning framework. The input from the camera is connected to the device and is evaluated using this framework. So if a weed is detected in the field, the device returns an alert to the user. And here is the output from that module of the device. So you can see you have 3 images: one's poison ivy, one's clover, and one's dandelions, and they all have the boxes around them that tell you what they are. So for some additions that could be added if we had more time beyond the scope of the semester, in order to increase the efficiency and functionality of the device, a GPS connection could be added, which would help the device to plan its path through the fields. A weed removal system could be added to remove the weeds identified by the device. And finally, a fertilization system could be added to autonomously add fertilizer to the crop when they need extra nutrients.
Thank you.
Thanks.